And are ready for another exciting day of discussions and collaborations. I'm Hamda Al-Hosseini, and it is my great honor to continue serving as your Master of Ceremonies for today's session. On behalf of the National Center of Meteorology and the UAE IREF, I would like to thank you all once again for your participations in this important forum. As we continue to explore innovative solutions for rain enhancement and weather modification, our sessions today will focus on some of the most advanced and promising technologies in this field. We have a packed agenda with keynotes, technical presentations, and panel discussions aimed at expanding our understanding of latest advancements in weather modifications. We begin our day with a session titled Advances in Autonomous Unmanned Aerial Systems for Weather Modification Applications, and this session will discuss the cutting-edge advancements in unmanned aerial systems and their role in enhancing rainfall efforts. This session will cover various aspects, including technology readiness, regulatory and operational constraints, and the potential for autonomous real-time decision-making in weather modification. To kick things off, it's my pleasure to invite Dr. Shawki Qasimi, the Chief Innovative Officer of the Technology Innovation Institute here in Abu Dhabi, who will deliver the opening speech for this exciting session.
Good morning, everyone. So, thank you for the kind introduction. Excellencies, ladies and gentlemen, distinguished guests, very good morning. It's a privilege for me to welcome you all to this important session in advances in autonomous systems. I think that it's one of the key technologies which we rely on to improve our seeding capabilities. Allow me first to express my deepest gratitude to His Highness Sheikh Mansour bin Zayed Al Nahyan for his vision and steadfast support for innovation and scientific research, which continues to shape the UAE into a global hub for incredible advancements. I would also like to thank you, the organizers of the Rain Enhancement Forum, for providing us with this invaluable platform to exchange ideas, insights, and innovations that will address some of the world's most pressing challenges. Today's session is about advancing technology. It's also about redefining what is possible. And the motto of the UAE is that impossible is just the beginning. We are here to disrupt and move towards the next capabilities and technologies that will disrupt the world, and specifically solve some of the critical challenges that we all are facing. The intersection of sustainability and technology offers us a unique opportunity to leverage innovation to tackle one of humanity's most urgent challenges, ensuring water security in a changing climate. And recent critical natural events have shown us that finding ways to improve our water supply security is of fundamental importance. Today's techniques are increasingly enhanced by emerging technologies such as autonomous systems, artificial intelligence, drone, laser-based applications, unlocking new possibilities. And we have seen recently the UAE becoming one of the top players in artificial intelligence, being the foundation for autonomous systems and autonomous technologies. These techniques hold the promise of addressing the global water security and mitigating the effects of climate change. For the UAE, this topic is of fundamental importance. Located in one of the world's most arid regions, the UAE has long been at the forefront of research and development in rain enhancement. Over the years, the country's leadership has demonstrated a profound commitment to ensuring water sustainability. This includes investing in advanced technologies and research initiatives, establishing the UAE Research Program for Rain Enhancement Science, and conducting large-scale trials of innovative techniques such as cloud seeding. These efforts underscore the UAE's forward-looking vision for managing one of the world's most critical challenge. While the UAE is globally recognized for its rain enhancement initiatives, misconceptions about cloud seeding persist. And this is something that we will all need to think about. How are we able to clarify to the world that rain enhancement and cloud seeding is not water manipulation, is not water and resources captures, but it's a technology, a capability that will help the world to prevent natural disasters. Firstly, cloud seeding does not create rain from scratch. It enhances natural precipitations in clouds that already have rain-forming potential. Second, the process is safe and environmentally friendly. The UAE uses non-toxic, salt-based materials that comply with the highest environmental standards. And lastly, cloud seeding is not responsible for extreme weather events. For instance, during the floods in the UAE last year, many speculated that cloud seeding caused by unusual atmospheric conditions and heavy rains unrelated to the cloud seeding activities. And this is something that we will need to advertise and explain to the general audience. The floods were caused by unusual atmospheric conditions and heavy rains, and top scientists have confirmed this event. Educating the public about these facts is crucial to fostering trust and understanding how these innovative techniques will help us prevent natural disaster in the future. Why do we need weather modification techniques? Water scarcity is a growing global challenge. The most water-stressed regions are in the Middle East and North Africa, where 83% of the population is exposed to extremely high water stress. By 2050, an additional 1 billion people are expected to live with extremely high water stress. Factors such as population growth, unsustainable water management practices, and the impact of climate change have led to diminishing freshwater resources in many parts of the world. Droughts are being more frequent, threatening agriculture, flood security, and livelihoods. Extreme weather events, including floods, increasingly endanger communities and infrastructures. Climate change exacerbates these challenges by altering precipitation patterns, intensifying droughts, and increasing the unpredictability of weather systems. Simply put, these challenges posed by climate change and extreme weather events make weather modification an urgent necessity. The growing need for intervention requires scientific research to develop scalable, efficient, and safe solutions. These complexities of water scarcity and climate variability challenge us to rethink traditional approaches, giving rise to innovative solutions that redefine what is possible. At TII, we are proud to be part of this global effort, and we are extremely honored to work with some of the best research institutions like yours to find ways, to find solutions to prevent climate change impacts and increase the water security for the UAE and the world. One initiative focuses on bringing up to the sky the sensing capabilities currently available on the ground from weather stations. Another one center on the use of drones to perform cloud seeding is actively working with the rain enhancement team here in Abu Dhabi. While many of these projects remain at the R&D stage, they reflect the UAE's commitment to find solutions. Another of our centers, the Directed Energy Research Center, is also working on a new rain triggering initiative based on intense lasers. Some of the results are shown in the poster session. And I just saw very interesting videos that Dr. Matras has done for some of the key experiments that will be released very soon. It has been working on a project focused on using those intense laser pulses remotely to induce controlled atmospheric modifications and influence precipitation processes. We have found that this laser-based approach is more efficient than the traditional cloud seeding techniques, but yet requires confirmation. And along with our autonomous and robotic center, we are focusing today on bringing cloud seeding the autonomous capability support. It's extremely important to understand that the UAE became the playground for cutting-edge technologies. Being able to have drones flying in the skies requires safety and secure mechanisms that UAE has been adopting during the last 5 years, making the UAE the best place to evaluate and develop key technologies based on autonomous systems. This system represents a new frontier in the field by combining advanced technologies with precise operational capabilities that we are collectively developing. They offer us a new horizon in environmental innovation, allowing us to reach a new potential with unprecedented precision. They turn science fiction into reality, enabling us to channel the power of nature itself to address water scarcity in a way that is both sustainable and scalable. By harnessing the agility and efficiency of unmanned systems, we are reimagining what is possible. As a result, performance in water modification application is greatly enhanced, and we are all contributing to this change. They are harbingers of a new era in environmental stewardship, where precision, sustainability, and innovation converge. Despite the immense potential of unmanned aerial systems, their integration into weather modification efforts face a few challenges which we must address. And this session will open our eyes on what key challenges we will need to solve to make those systems fully operational. By addressing these challenges together, through innovation, collaboration, and policy support, I'm convinced we can see the full potential of unmanned aerial systems for weather modification. This leads me to the importance of collaboration. Collaboration lies at the heart of progress, especially in this field, and UAE is a reflection of this will to collaborate by sponsoring, financing research groups from all over the world to advance knowledge and innovation in this field. As we embark today's discussions, let's embrace the power of collaboration and innovation. Together, we can turn challenges into opportunities and innovation into tangible impact. Let's live with a renewed sense of purpose, united by the shared vision of a future where water sustainability and water security become global realities. Thank you for your passion, your expertise, and unwavering commitment to advancing progress in this field. Finally, before closing my presentation or my talk, I would like just to give you an interesting coincidence. The presentation was supposed to be given by Dr. Najwa Araj, our CEO at TII, but she is currently flying in another country to deploy unmanned systems for mangrove seeding. And this is again one of the key commitments that we have as an organization located in Abu Dhabi in supporting the region and the world in preventing and protecting natural resources such as mangroves and water. Thank you very much, and I hope that today we will have fruitful discussions, and if you have any questions, please let me know. I will be sitting here. Thank you very much.
Thank you, Dr. Shawki, for your remarks and for setting the stage for today's discussions. Before I invite our presenters to the stage, dear audience, please submit your questions using the QR code, and our moderator will be sure to address them during the wrap-up panel discussion after all three presentations are completed. We now move to our first technical presentation of the session. Please join me in welcoming Jan Hamburger, Research Group Leader on Experimental Cloud Physics at the Swiss Federal Institute of Technology.
Yes, welcome also from my side. Thank you for giving me the opportunity to present our work here, which we are doing in Switzerland and using a UAV of seeding low stratus clouds. Yes, and I will start with very basic. What is actually the working principle of glaciogenic seeding? So you inject ice nucleating particles inside the clouds, they form ice crystals, and then grow by diffusion first, later also aggregation or riming, and then forms the precipitation, which you would like, if you want to do rain enhancement, like to use. But when you look at the report from a World Meteorological Association, they stated that exactly these processes of formation and growing of ice crystal, we have large unknowns and uncertainties here. And that started to think me, oh, that could be beneficial for both sides. We have to learn more of these processes if we want to do better rain enhancement, but also for natural cloud, can we use seeding as a tool to learn more of natural clouds? For me, I was a bit critical. Does it actually work? I mean, history is that there was a large optimism in the 70s. We can really change whole cloud systems. As an example, where they used dry ice to burn a hole in it. It didn't work out as well as thought, but the Snowy campaign, here's a publication of French et al., really showed very convincing that glaciogenic seeding works. You clearly see the radar reflectivities increased by glaciogenic seeding, marked with an error here. But I was wondering why they reported only 30 minutes after seeding. Does it take so long? Is there a time delay? What actually happens in the first few minutes? And that's where the Cloud Lab project was started. So as a disclaimer, I will not look into rain enhancement, but really focusing on the first 10 minutes. What actually happens if you inject ice nucleating particles, and then how does the ice crystal grow afterwards? So yes, Cloud Lab project was an ERC-funded project, which was very important because it was a quite big project to be able to perform this. We've been out the last 3 winters in the cold in Switzerland, so normally I would standing right now somewhere in the snow, and it was quite cold outside. We used a drone for seeding and a second drone for also aerosol measurement, and tethered balloon system for the in situ measurements, including a holographic imager for the cloud properties, and a lot of remote sensing instruments. So I'm very happy that some collaborators joined us, so we collected up to 5 cloud radars to measure then the effects of the cloud seeding. So Cloud Lab project the idea was to study ice formation and grow in the first few minutes, and using seeding as a tool, so we could know exactly when we inject the particles, where and when, and so when the ice crystal formed, and then measure it afterwards on our main measurement sites. And the UAV gave us the possibilities to also change the location and the distance between the seeding and the measurement. So yeah, for distance it means also we measure the cloud changes, for example here, 7, 8, and 9 minutes after seeding, and could compare what was the effect of the seeding. First thing so we used mathematics meteor drones for seeding and silver iodide containing flares, quite standard flares, which are used also for hail prevention in Switzerland. And the first thing you might ask, oh, flying with a UAV into super cool clouds, what's about icing? So yes, we had icing, and icing is dangerous because what it makes, icing collects on the rotors, and here it needs more and more power for the UAV to stay in the air, and if it gets too much, it crashes. It actually happens to me. I crashed one of our UAVs. Luckily, it had a parachute, and the damage was limited, but I was not allowed to fly anymore afterwards, so only our female pilots now flew the drone, so I can say we have really an unmanned aerial vehicle. But yeah, luckily what we have, what I should have done is do the heating of the rotor, so we have a heating system. You see a spike in the current needed, and afterwards the current to fly went down, so we de-ice the rotors, and then you see it starts again rising. Icing forms again, and you have to repeat the cycle many times. It limits your flight time because you need more power, but you can fly safely in super cool clouds. And Anna Miller actually then did a nice study and looked on the slope, how fast is rise, and showed that the icing severity depends on the liquid water contents mainly, and a little bit if large droplets are present. Okay, did it work? That was the next question. And because we used only one flare, 20 gram of ice-active material, is it enough to change a cloud? And before I go into scientific data, I thought an image is always good. So on the left side, you see an image of our measurement site. You see actually nothing. It's in the cloud. But when the seeding plume came over us, suddenly blue sky appeared, and we saw a test balloon flying. That was a great, little bit also scared feeling to see you can really change a cloud and suddenly have blue sky by our action. And in addition also, it's probably not too best seen on the right, small ice crystal were precipitating down to us only in this 5 minutes, and afterwards sky came again and we were again inside the cloud. Okay, scientific data. Here's a radar reflectivity of the seeding mission. The seeding mission, beginning of the seeding mission are marked by a star. You see clearly the radar reflectivity enhancement from 10 to 25 decibel. The number means the distance of the seeding to the main site. So we did 3 experiments, 2,000, 2,500, and 3,000 meters away from the main site, and the radar reflectivity increased with distance. And in particular, in the last mission, you also see sedimentation starting. Yes, but keep in mind, it's only 6 to 9 minutes. We measured the clouds only 6 to 9 minutes after injection of the particle. So it's quite fresh, and we were very surprised to see this large increase in radar reflectivity. In addition, we had also in situ data on the tested balloon. The flight path is shown with a black line. And then we can actually look what happened to the cloud microphysics. And that is shown here. In blue, the droplet concentration, and in red, the ice crystal concentration. In the background cloud, there were 0 ice, and then through the seeding, we created up to 1,000 ice crystals per liter. And at the same time, the liquid phase got depleted. So that is the Wegener-Bergenow-Findeisen process in action. So now we can compare also the in situ data, the ice crystals between the 3 seeding experiments, and you nicely see, okay, they get bigger and bigger if you see further away, so they had more time to grow. And this allowed us now to actually calculate ice crystal grow rate by taking the size of the ice crystal and dividing by the residence time of the ice crystal, so the time between seeding and measurement. And Christopher Fuchs then took all our experiments where we had good data. It was 16 experiments between -5 and -8.5 degree, and looked how fast did the ice crystal grow. And we could nicely, if we looked at the major axis, could nicely see a transition between a blade regime at a very cold temperature and to the needle regime where you have enhanced growing in the long direction, which is also expected. It's known from literature, but normally you have to go into cloud chambers to measure this. It's not possible to measure ice crystal grow rates in natural cloud because you never know, if you measure an ice crystal, how old it is. When was it formed? And seeding helped us, or it gave us a tool to know when it was formed. What was the freezing mechanism of the ice crystals? That is the next question. So we looked first at the seeding concentration and compared it how many ice crystals was formed, and we found a very nice correlation. So the seeding particles really created the ice crystals, and we were a bit surprised that we never saw a plateau, so never overseeding was happened, so always the same percentage of ice crystal formed ice. We're not yet sure why, but I'm still surprised and puzzling by this fact. But then when we compared different experiments and looked at the ice nucleated fraction, so how many of our seeding particles actually form ice, we showed it's only 1%, and it's also not depending on the cloud droplet number concentration, which for us that rules out contact freezing, because then it would be a strong dependence on the cloud droplet number concentration. We also don't think it's immersion or condensation freezing, because in existing clouds you don't reach the supersaturation for activation of the seeding particles. But what we think happen, the seeding particles are quite hygroscopic, so they grow and form dilution droplets, and this then freeze by immersion freezing. Okay, that's what we learned about the formation and growth of ice crystals. Then we also say, okay, what can we use? How can we use with the data? Does a model reproduce our experiment? So we did an icon large eddy simulation with quite fine resolution, 130 meters, and made a directly comparison, so same day, same location, as our experiments, which is in itself not a simple task, because sometimes the model don't show a cloud at all or something, but it worked quite well. 2-moment microphysics, a special seeding parameterization for the seeding particles, and to repeated the seeding experiment in the model. So we tuned the model that it's producing the same ice crystal concentration as observed in the experiment, and then looked what is the liquid phase doing. And if you look at the top, that was actually the time of the measurement. You see in the observation you have a depletion of the liquid droplets up to 100%, but the model only had 25, maybe 50%. And you have to have 10 minutes longer in the model, in the lower panel, to achieve the same reduction, which means the model is too slow in reducing the liquid phase, and we're right now trying to account for turbulent motion by changing the ventilation factor to bring the experiments and the model in agreement. Okay, and with this, I come to my conclusion. It was a great project. We did have now data of 70 glaciogenic seeding experiment with really clear data. My conclusion is that seeding with UAV works, but you need a good de-icing mechanism, particularly in supercooled clouds. But it gives you a very cost-efficient method of precise and localized seeding experiments. The payload still limits the amount of the seeding materials, but you could also think about going to fixed wing or using multiple drones. And I like that we were able to observe natural ice crystal grow rates, which you normally have to go into a cloud chamber, and had this really good comparison between our seeding experiment and the model world, which is also not a given. And with this, thank you.
Thank you, Dr. Hamburger, for an insightful presentation. Audience, please continue to submit your questions via the QR code, and we will address them during the panel discussion. Next, we have Vasil Strait, researcher at Active Interventions in Atmosphere, an entity based out of Romania, to share his expertise.
Hello, Your Excellencies, ladies and gentlemen. Today I want to present you on our research in exploring fixed-wing UAVs for cloud seeding. My presentation have 5 parts. A few words about our activity, the drone concept, advantages and opportunities of this new approach, and the research for future development. A few words about our company. We are a company that contributes to mitigate the effect of climate change that can affect agricultural crops in Romania and safety of the population. We are focused on hail suppression, rain enhancement, and specific specialized training. Our main activity is hail suppression using rocket technology. We do that for 12 years. Also, we conduct experiments for rain enhancement using aviation technology, small-scale experiment, 4 years. With short time experiment and small scale experiment. We also conducted experiment with growth generators for rain enhancement with helium balloons. And now we concentrate our efforts to develop this fixed wing drone. Also, we have radar system and software that analyze radar data. Our drone concept, we try to respond the limitation of the traditional cloud seeding method. We developed in this fixed wing drones, designed especially for cloud seeding. It's currently at technology readiness level 5 to 6, and undergone extensive flight tests to integrate this on the final configuration. It's a wingspan with 5 meters. It's a big drone. Maximum takeoff mass 120 kilograms. Flight speed 100 to 200 kilometers per hour. Controllable by mission planner from the ground remote pilot. An autonomy flight for 4 to 5 hours, depending on the environmental condition. Range 150 kilometers, or turning radius of minimum 80 meters. It's equipped with an engine with 2 cylinders, and time between overhaul more than 700 hours. Of course, the drone have its operational limits. Operational ceiling is 5,000 meters. Temperature to minus 30 to plus 50 degrees Celsius. Humidity all range. Wind speed maximum 50 miles per hour. And an electric field strength maximum kilovolts per meter. Okay. Here's a short movie. Think. Don't. Sorry. I think don't play the movies. Okay. I started. We have a protocol, collaboration protocols with Republic of Moldavia, our neighbor, and developed there this drone. And we are allowed to make test flight, and also have protocol collaboration with their weather modification agency. And in the near future, want to make some tests by seeding clouds in real environmental medium. We conducted a few flight tests and discovered some issues. And now our engineer developed this drone to make it suitable for the next developing process. A navigation software, it's Ardopilon software suite with mission planner ground, display radar, display real-time data, UAV performance and position, and can be used as a virtual cockpit. Interaction with and cloud seeding application is designed, how I say, for cloud seeding application. Can carry an additional payload up to 80 kilograms. It's a huge capacity. We don't need this for now. It's equipped just to transport 40 smoke cartridges. It have a de-icing system for engine, propeller front engines, bearing surfaces. Also, it's equipped with a dual frequency GNSS navigation system, compatible almost with all satellite constellation. Also, we tested very well cellular and satellite connection. It's optimized for takeoff and landing of unimproved runways as short as 150 meters. Installed sensors. For now, they have just the air temperature, humidity sensors, wind sensors, and position, real position sensors. We plan to install a backscatter probe with polarization detector, but we will see in the future if will be the best, our best choice. Advantages and opportunities of these new technologies, compared with traditional seeding method, we thought that can operate in reliable and diverse and challenging conditions, including daytime and nighttime operation. maybe the flight cost will be lower compared to airplane flights. A new avenue for making cloud research, visual detection of seeding signature by high-resolution videos, research for future development of the drone. We want to demonstrate this prototype in operational environment in the next 6 months. We want to have certificated for this drone under ACAO requirements. We want to install the sensor to measure size distribution of water and ice particle, and also to make experiments to enhance the precipitation in the Republic of Moldova and also in Romania or other parts of the world. So, thank you for your attention.
Thank you, Dr. Hamburger, for your insightful presentation. Audience, please continue to submit your questions via the QR code, and we will address them during the panel discussion. Next, we have Vasil Strait, researcher at Active Interventions in Atmosphere, an entity based out of Romania, to share his expertise.
Thanks, Vasil. That was a nice presentation. I'm Roelof Berger, and it's really a pleasure to be here. Once again, thank you to the organizing committee, Alia and her team. Every year, you raise the bar and exceed the expectation. It's really nice to be here. What an exciting topic that brings us together here this morning. It's not only fun to play with and very dangerous in the wrong hands, but I believe that this technology can really help us to answer one of our most pressing and difficult challenges in specifically convective cloud seeding. And that is placing the seeding material at the right place at the right time. So if I can remind you of our warm phase seeding conceptual model, we see there the first step in identifying the treated storms. We think of the nice talk we heard yesterday by Luca, and also the new project by Danny and his team that's really delving into how we can use the cutting edge of science and technology to improve this step in our process. But the second one, applying the seeding agent, in my mind, is one of these challenges that we don't talk enough about. And frankly, I blame people like Marwan that comes and tells us how difficult it is to do these modeling studies and setting up the model and getting the tuning correct. But then when they model the seeding effect, they just magically place the material there at the right time and the right place. But if you really want to know how difficult it is, you have to speak to people like Jim or Ahmed or Sufyan, look into their bloodshot eyes and think about how difficult it is to drag pilots out of bed, get them at the airport, fight with a tower to get the aircraft in the air, fight with traffic control to get the aircraft close to the clouds. In fact, I think that every time we put a seeding particle even close to a cloud, it's a miracle. And you can see that if we don't do that job right, all the dominoes can't fall. I struggle to find people that have data for us to quantify how effectively we place the seeding material. And the only paper that I know about is one that we published. It's a paper by Dion in an obscure little journal in South Africa, but available online, the Water Essay 2005. And in this study, we did a semi-operational project for a year, and we could only get close to about half the storms that we thought were seedable cases. And then of these, we only could seed around 17% of the storms. And this is in a remote location with a very well experienced team. And you can imagine in places like the UAE with its very heavy air traffic, that efficiency will likely be much lower. The project I referred to is that one on the bottom left, and here I try to indicate another way that we can understand this challenge. You can see there's different randomized experiments where we treated some clouds seeded and not seeded, and if you compare those storms, you can see that it appears that the seeded storms seem to live longer. Well, in the bottom right experiment, I did a theoretical case where instead of seeding the storms, I just made a small error in the decision of which storms will be seeded, and a 6-minute delay gives us a similar impact. And this illustrates to us how difficult and challenging this job is of putting the seeding material there at the right place at the right time. So we can think about all these challenges of manned aircraft, the inefficiency, the operational restrictions, especially in a place like the UAE, and then the risk. In my short career, I've been involved with 3 projects where there's been aircraft crashes. At least in 2 of those, the pilot survives. And then also the cost. So we can dream about what unmanned vehicles can do for us. Having a swarm of these vehicles will give us a much better coverage. Having distributed launching sites, maybe mobile stations, can also give us much faster and adaptive response. We can also maybe get past the operational restrictions by having very well-defined areas that we operate in, and then there's the obvious reduced risks, and then maybe not immediately, but in the future, we can live in a world where the costs are reduced. This program funded a project where we did a pilot study. You can see the publication that describes the project in atmospheric research. It was led by Eric Frew from Colorado University, and I was a co-PI on the project. What we did, and you can see there, we separated the problem into 3 components. The top left is the first part, where we have to use all the available observations and all these new fancy techniques like Luca mentioned to try and see where is the next potential seeding target, and then cleverly trying to navigate the aircraft to the best. The second task in the top middle is the vehicle that then has to map this area and try and find where is the updraft area that is appropriate for seeding. And then the third component is then using in situ observations to really confirm and answer the question, are we really in the right place and at the right time? And during this project, you can see we had a few successful cases where we could operationally tie all these 3 components together and then show how this could be done. The bottom right picture shows one of those cases. The blue box is the area that was identified by the ground-based observations, and then the 4 panel shows the in situ data, and the top right-hand panel, you can see those green bars indicating that the aircraft did detect a seedable area. The animation on the right shows the typical radar picture. You can see the storm system moving over, and you can see first the mobile station moving into the right place, and then the launch of the vehicle. Unfortunately, we couldn't do this experiment in the UAE, and fortunately, it's much easier to do it in the kind of environment that we had in the US. You see these very well-established convective systems with the individual cells sort of giving us the opportunity to place ourselves in the path of this approaching system and then waiting for the right opportunity. Things a little bit more challenging here in the UAE. So for the rest of the talk, I thought let's try and then define, if we wanted to do an experiment like this in the UAE, what would this target area look like? So on the map there, you can see small little dots of all the storms that was detected over a 10-year period. Those would be the very light dots. And then I highlighted in teal the dots that we think is the kind of area that we have to target. And you can see we think that the Haja Mountains is maybe the best place. Not only is this one of the most important areas for rainfall in the region, but it's also a very well-defined area. And the storms in this area, especially during summer, gives us a little bit of a higher predictive skill. So we need to then look at a subset of these storms. So all the storms were in the order of about 10,000 potential candidates. But if we limit our inclusion criteria to storms that actually live long enough to produce precipitation, and they show a time period where there's consistent growth, that number drops down to in the order of 100. So orders of a magnitude fewer realized opportunities than what there are. This is the statistics of these storms, and you can see there on the left the histogram of the storm duration, and on the right I show you the probability of survival in the orange curve as a function of storm duration. And what this graph tells you is the challenge of finding one of these 1 in 100 storms that has the dynamic environment that will make it sustainable to live into a bigger storm. We could be very optimistic and say maybe we can convert some of these unrealized potential storms into real storms. But first, we have to be able to detect and then seed storms in a very efficient way. If you're interested in this kind of stuff, ad break, Michael Weston has a nice poster outside, and you can visit him after lunch and delve deeper into the storm statistics for the UAE. So here's an example of one of these events, and now you can compare that with the US case where you saw that this big, large-scale system moving over. Here we need to wait for this magic time where the storms start popping up. And if we have manned aircraft, you need about a 2-hour warning for launching the aircraft and making sure that you're in this area. You can now imagine how much easier that would be if we had drone sites all around the mountains and having much greater response. For cloud-based, we can look at statistics from radiosondes, and here you can see for the Muscat and Abu Dhabi sites, we're looking at cloud bases of between 1 and 2 kilometers. And then to try and estimate what are the speed and areas of these targets, here's a frequency histogram of mean storm speeds for these ideal cases in our area, and then also a frequency histogram of storm area. And this gives us important information about if we have a UAV and we want to map out an area to find the very special updraft region. This is the kind of area and the movement of this target area that we have to look for. So how many of these opportunities are there in a year? You can see there how these numbers fluctuate over the 10 years of data that we've looked at. And then on a particular month, you can see that it's a handful of storms that you will typically see in a month. Now, this looks a little bit bleak, but it might fill you with confidence, and you would say, okay, that's not so difficult. If with a good amount of planning, we could target these storms. But if I now add all the storms detected, not just those that lived long enough and showed good growth potential, you can see there's the orders of magnitude more storms per year. And if we look at the number of storms per month, there you can see, okay, now it goes up to about 20 storm days during the summer months. And then the number of storms per day, you can see between 2 or 5 storms per day. And what I don't show is if you look at how, in a typical hour when we do have storms, how many of these storms would be concurrently observed. You get a number between about 3 and 8 storms at the same time. And there we have it. These would be like the design criteria. If we have to imagine a UAS that is cost effective but also able to find these targets and delivering seeding materials, this would be the kind of statistics that I propose we establish. We also have 2 posters. Mohammed Kasim has it there. You can visit us after lunch and discuss more about some of the proposed strategies that we can use to look for these target areas. And then I also want to use this opportunity to invite you to the WMO meeting where we can continue this discussion, which will be held in November in India. And if there's any one of you that wish to get more involved with the organization, maybe chair a session, we would be welcome to approach me. We can discuss it. Thank you.
Thank you, Professor Berger, for the enlightening presentation, and apologies for the earlier misreference. We now move to the panel discussion where our esteemed experts will explore the diverse challenges and opportunities in the use of unmanned aerial systems for weather modification. Please join me in welcoming back our 3 presenters and the moderator of the panel, Dr. Dion Terbelach, member of the IREF Strategic Direction Committee.
Can you hear me? Yes, you can. So I hope you had a good night and you enjoyed the presentations this morning. I thought they were quite insightful, and we clearly have now moved into the era of unmanned aerial vehicles, and we see that in different ways around the world. Some of them not that pleasant, but it still shows you the potential of this technology. And we heard this morning and saw this morning how this technology is already being used in our field, and this is really exciting. I was thinking when I listened to Rudolf's talk this morning how we, about 20 years ago, started looking at UAVs in South Africa, and all the complex meetings we had with the Civil Aviation Authority, trying to convince them that, you know, the time has come to think about regulations to allow the use of this technology. And unfortunately, in many parts of the world, that issue has not been solved. And I think that is also a priority to look at. So let's start with the questions. And I think the first one that we're going to start with is with Jan. Your research delves quite deeply into innovative platforms like UAVs for atmospheric measurements. How do you see the role of UAVs evolving in cloud seeding operations, especially in advancing precise and localized interventions? As you know, we've now celebrated 10 years of this program, and now we're looking at the future. So looking at the future, and especially taking into account that we also deal with convective storms. So if you could give your insights in that, Jan.
Yeah, thank you. I think UAVs in principle are the future, as they can bring very localized and very specific seeding operations. What I thought it's interesting is what you can do with UAVs is actually you can have multiple of them and also have multiple UAVs in the same cloud. And this allows you to answer very specific questions. For example, what is the best place to put the seeding materials? Why not use multiple UAVs at different locations and see what is the best approach, or different seeding materials, or sizes of the seeding materials, or very interesting questions. So UAVs, you can have very specific questions, but you might go back from really the operational approach to a more scientific approach of answering a question. And yeah, one issue is still a limited payload. but that could be also an advantage. So you also limit the amount of materials you're bringing in. So you can be more precise. If you know where it's best, you can be more precise what area is affected. And yeah, that are my thoughts about it.
Okay, thank you. Vasil, can you tell us about your experience, seeing that Romania has had such a long history of aviation-based precipitation, enhancement, hull suppression, and so on? What are the specific lessons and suggestions when you want to integrate UAV technology into such existing weather modification frameworks?
Thank you.
Thinking about the staffing issues, the manpower, and all that, what are the challenges when you introduce a new technology like this into an existing program based more on the conventional approach using conventional aircraft?
Yeah, thank you. We have some experiments with aviation, not such great like other countries, but we learned some valuable lessons. I think, first of all, with the drone can increase the flexibility of operations, can increase also I don't find my words, sorry. Increasing the flexibility because we can deploy the drone quickly on the area and can have the windows of opportunity for seeding clouds. And also it's safety issues will be resolved because we don't be involved the human on the airspace also. And then our first thought is that the cost will be lower than that involved using managed airplane.
Thank you. Rudolf, you've been involved in quite a number of international rainfall enhancement projects over the years. You mentioned a short career, and I know that that's not really true anymore. So from your experience, what are the most pressing challenges in scaling up UAV technologies for operational weather modification programs in diverse geographical and regulatory contexts?
So I think you put your finger on it in your introduction. The challenges are not really with regards to the technology. We've seen studies decades ago using cutting-edge observations on these platforms for better looking at numerical weather prediction, making observations in difficult places like hurricanes. So for me, the biggest challenge is regulatory, like you mentioned. And I still think it's underappreciated. In our project, for example, we really tried to do the experiment in the UAE. And in the initial stages, all the parties were very positive about it. But in the end, it was issues like exporting restrictions, bringing this technology into the UAE, and then also being able to fly in the area that you want to fly. It's one thing to go to an island somewhere remote and do these experiments, but let's say we have this Haja area that we really want to see if this can work operationally. Getting permissions to fly there is really a challenge. I think the committee should really ask these questions for potential proposals, and this should be one of the things that we figure out before we actually promise to do experiments. So specifically in the UAE. That's why when we look at the Romanian experience, there seem to be parts of the world where this is a little bit more easier, and maybe we can use those opportunities to try and develop the technologies.
Yeah, I think this is really an issue that would probably need integration of our community with other communities that are also dependent on the use of UAVs and its development into the future, and work together to try and sort out the regulatory issues, because we really need to tap into this great potential that this technology gives us. So something to, and I agree, it's not a technology limit anymore. It's definitely not that. I think we can achieve everything scientifically and technically that we would like to do, but it's to be able to operate safely for all parties in the desired environments that's really the issue, with the proper permissions. We've had quite a number of questions also from the audience, so I thank you for that. And the first one I want to address to Jan again. Did you measure the chemistry of the concentration of silver iodide after the cloud has evaporated, in other words, downstream? And if you did that, do you think you can even use less seeding material to achieve these results? Can you, in other words, can you further optimize the effect that you've seen by using less material?
So far, we only measured size distribution of the aerosol particles and not the chemistry of the seeding particles, but it's definitely something we want to look at it and also collect cloud water or the precipitation and analyze them, how much seeding materials they contain. And absolutely, I agree, we want to try less seeding materials, because for the first try, we for sure wanted to see a signal, to be sure we see something, but we're also surprised of the strong response. So now the idea with what happens if we reducing seeding material, yeah, I'm curious. Yeah. It should still work, and it's yeah, it's a very, yeah, it's almost too strong, our response. So yeah, would be interesting to see.
Yeah, I think it's the important thing, because as we move into the future as well, we need to optimize how we use seeding material, and it's not just about placing it in the right place at the right time, but also the right quantity and not wasting seeding material. Because as we know, despite many studies showing the opposite, that there's still suspicion around silver iodide and its environmental impacts. So it's always important to do those measurements just to address those issues as well. So another question that I have here, and maybe Rudolf, you can help us with this one, is what are the latest advances in autonomous cloud seeding technology, and how does AI, how is that being integrated into weather modification on rainfall enhancement efforts? How do drones and autonomous aircraft contribute to modern cloud seeding techniques, combining also these other new technologies that we've also spoken about yesterday in this forum?
Yeah, AI plays an important role. The first thing that we have to do, the first step in these projects, is to identify when and where you can expect these opportunities. And as Lucas has showed us yesterday, AI has helped us to make huge strides towards improving that. There's also a little bit of AI involved on the UAV system that we designed, finding the best route towards these areas, and then also to make the decision whether it's a seedable storm. But answering the question, what is the next big thing that UAVs can do for rain enhancement? I would say delivering the material efficiently. Many of the pressing questions that we want to answer, we can't, because we just can't set up these opportunities easy enough. So it's one thing to, in an operational project, to try and find as many opportunities as possible and then seed those storms. It's another to try and set up a science experiment and get maybe secondary aircraft ready to make observations, and then seed that specific case in a fleeting environment that we have, like here in the UAE. So for us to answer questions like, firstly, the study that was shown by Jan from French, if we want to directly measure the seeding signature, we first need to be able to set all the pieces of the puzzle in place and then efficiently go and seed that cloud, which is a challenge. If we want to answer questions that you ask, how much seeding material is enough, we first have to get to a point where we have the luxury of choosing how much seeding material will we put into the cloud, and do it so efficiently that we can get enough cases for our study, and where we have a dose-response kind of relationship. So for me, delivering efficiently seeding material is the next big question for convective clouds. And I just I'm a little bit jealous of Jan, because those environments are a little bit easier to work in. The window of opportunity is a little bit more wide, and that's what the challenges are. And especially in our arid environments, where these opportunities are so fleeting, that you need to have a very good plan using all the available technologies, including AI, to make sure you can reach those.
Yeah, it's a bit of an understatement to say that it's a slightly more simple cloud system. This is almost as close to a cloud chamber that you can get in nature. And I've got a question related to that. Did you see, Jan, any indications of ice multiplication in what you were doing there?
I would love to. It would be my dream to trigger in a controlled way ice multiplication in a cloud. That would be very happy. So right now not, and we think because we neither have big droplets nor existing ice crystals.
Okay.
And for most of the processes that is needed, we were surprised that we have cases after 8 minutes or 10 minutes, we see quite heavily rimed already. That happens, but I'm happy to discuss any ideas how to trigger secondary ice process. I would love to try this.
Yeah, of course, it's a process where we still have a lot of questions, so if you have any opportunities to contribute towards that, it will be of great help. And it's a really important process. Let me see, there's more questions from the audience. This relates to how do you believe this, and this is to all of you, anybody, how do you believe this technology can drive global innovation and collaboration? I think we've already mentioned this issue of how maybe one can work together with other communities in addressing the regulatory issues, but you can elaborate on that. Rudolf?
I think one of the outstanding features of the UAE REP program was how it's been able to bring together, scientists from all over the world. We heard yesterday 76 nations involved, the top scientists in the world competing for these events. So not only that, but also when we see that the ultimate aim of this program is to actually plow back into the global village and improve this science for everyone. And then when we think of this technology and we think of these regulatory restrictions, it poses a very specific problem for how can we advance UAV application to the science in a program like this. And I think that this may be one of those projects where we have to look for opportunities to work together and maybe do multiple experiments in different nations under different kind of regulatory environments to see if we can improve this technology, not only for the UAE, but for the world at large.
Anybody else would like to add to that?
I think it's kind of a must to work together international, because it's very tough for a single group or a single country to have this operational cloud seeding this operation. So it's, if someone can provide an area where it's easy to try out, for example, new UAVs, where it's much easier regulation-wise, that would be very beneficial for the international communities. Or provide UAVs where people can bring their instrument. I think it's still much easier to put an instrument on a UAV than on an airplane. You are still a level. It's still quite a lot of regulations to do, but one order of magnitude lower than in an airplane.
And I think the great advantage of UAVs is it forces us also to miniaturize and to optimize instrumentation, looking at weight, size, and all those things. And I like the idea of being optimal when dealing with issues. And I think this program in the UAE provides an ideal platform to discuss these type of issues that we just spoke about now, and maybe think about ways how to address even better the international collaboration needed to fulfill the full potential of the technology. And I was just thinking also that we've got a few members of the WMO expert team on weather modification, Rudolf also being one of them. That's another forum where if the community feels very strongly about this issue, it can be taken up, discussed, and it can maybe be brought before the Executive Council of the World Meteorological Organization, where the members can actually then help to deal with such issues if you feel really serious about this. And I would recommend to investigate at least those type of options. Let me see. So there's a question about whether there are any technical challenges being faced when operating multiple UAVs in the same cloud, or is it very easy to operate two or more UAVs closely? Waisala, I'll maybe address this one to you, but maybe Rudolf can also add to that. You want to? Basil, you can go first.
Multiple with...
Yeah, if you have more than two or more sort of UAVs, is it difficult to operate them fairly close to each other, maybe in the same cloud?
That things, I don't know, it's, we have to see if regulation permit these things in every countries, first of all. And after that, we can use AI and remote control software. Maybe in the next time, I think the technology will develop very fast, not only for this purpose of the drones. Globally, the drone technology is developing very fast, and I think that will push the authorities to change the regulation. And I think in the next 10 years, we will be able to fly it, manned and unmanned planes in the same aerial space, in the different fly levels, in safety for all the people.
Rudolf, you want to add something?
That actually makes me think of a different question. So it's an interesting thought experiment that links to Jan's presentation. So typically when we see these clouds, we have two of these processes that we can try and change. So in the convective clouds that we see here in the Middle East, we have the warm process, and we would typically see those at cloud base with hygroscopic nuclei. But then we can also try and change the ice processes. And there is two ideas around how to seed these. Sometimes people fly in the region where there's the most efficient growth of these nuclei, around -5 to -8 degrees Celsius. And sometimes they release the ice nuclei, but at cloud base. Now, when we think about what is the best way to deliver the seeding material, the cloud-based environment is a much easier place to target. We don't have to worry about de-icing. Having multiple vehicles in this area would also be much easier because there's not so much turbulence as in the middle of the cloud. So thinking about Jan's presentation and the modes of
activation of these ice nuclei. It seems that your study may suggest that targeting cloud-based, even for ice nuclei, might be a good strategy.
Thank you. Rolf, while you're busy, can you maybe just shortly give us an idea how, in the context of UAVs, the decisions are being made autonomously to make the decision where and what to seed? Shortly.
So we have measurements of aerosol concentration. From that, we estimate what is the CCN population, and then we relate that along with the updraft into a little model that try and estimate if we place ice nuclei of this size, would it effectively change the population to enhance the coalescence processes. So that was the little program that was running on the drone, making the decision yes or no for seeding.
Thank you. That is efficient. So I've got a question here about the duration and range of UAVs. We know from what has been done in terms of hurricanes that some of these systems have got extremely long durations. So, as we said before, technically there's actually no limitation anymore. And from all the seeding techniques and material we know about today, there's probably not even a limitation on which ones can be delivered from a UAV, from charging of particles to hygroscopic seeding to silver iodide glaciogenic seeding. So really, technically, there is not really much limitations. If we get our hands on the technology that's really available. So let's go back to Jan. Your work involves designing and developing new scientific instruments as well, including holographic imaging. How might advanced imaging techniques contribute to refining UAV-based cloud seeding techniques and understanding microphysical cloud processes?
I think it's an important question that is not only the delivering of the seeding materials and also measure the effects of the seeding. And best thing is you have in situ probes and probably even imaging probes. An image of an ice crystal gives you so much information, the shape, or we have now an algorithm to count the number of ice crystal in an aggregated ice crystal, so how many pristine ice crystal was formed from. And as we learned in the workshop before the cloud prop workshop for the last in South Korea, mostly the used probes are still technology of the 70s, the OAPs, and they have a lot of limitations, and I think the community agrees that they are really pushed to the limit, and I'm very convinced that holographic imager can be a step forward. It's quite tough to analyze the data, but nowadays with emerging computer technology it's feasible, and they're possible to get miniaturized to 1 or 2 kilograms. So they work also on UAVs, and they have the big advantage. You don't have to know the aspiration speed. So they work also on platforms with varying, fluctuating aspiration speed. So there's a good opportunity to put them on UAVs and improve our possibilities to detect changes in the cloud physics.
Yeah, fortunately, nature is really fascinating, especially when it comes to the different phases of water and the ice phase and how crystals develop at different temperatures and at different humidities. So we can learn so much by looking at images, and it gives us the history of how it was formed and how it grew. So it's really really important that we keep on top of understanding and keeping in mind all the science in cloud microphysics when we deal with this and use that to our advantage. Vasil, again to you, given your role in hail suppression and rain enhancement, what operational and logistical considerations should be prioritized when incorporating UAVs into programs? Say in the UAE, for example, what can you think of? I would like you to also think about manpower issues. What additional skills is needed and how best to acquire those as quickly as possible?
Yeah, first of all, if we want to make it operational programs, we can base it on a few scientists to make it this all. We have to have a good training for personnel who operate the UAVs, pilots, radar, meteorologists, and aviation contact with aviation authorities. Also, we have to be sure that in case of glaciogenic seeding, the UAV will not crash because of the icing, and to make intensive tests with referring at our drone. It's a big drone and can be equipped with the de-icing system. Also, this aviation regulation, it's the main problem, I think, in the present. We speak with our aviation authorities and we try to fly this drone to fly this drone on 1,000 meters, on 5,000 meters ceiling, and with scientific scope or something like this, to be allowed to use it.
Yeah, so I think that's another opportunity that all of us being here together, we can talk to each other and we can talk to colleagues like Vasil, where this technology has become sort of becoming embedded in a more operational way, and find out how they approached it, and let's learn from one another. So to all the panelists, I would like you to think about the future and imagine where we would be in 10 years' time incorporating this technology. Just give us your vision, and Jan, I will start with you.
I envision that we have really areas where we have multiple drones, autonomous flying with an automatic charging system, so they can be, no one has to be on site, and can be used either for operational cloud seeding or answering specific questions about understanding more the processes for rain enhancement.
Yeah, I think I can see that. Vasil, you have a vision in 10 years' time where we will be with this UAV technology?
Yeah, I think that, how I say, the things will happen very quickly the next time in this direction. And I think that using on fixed wing or another type of drones will be useful for this part of weather modification science. And the collaboration, I think it will not be any issues in the world in the next time. Collaboration will increase between the scientists because the community is not so big, but it's enough to have a weight in the scientific world.
Rudolf, your turn.
Well, I would say the only other way to effectively deliver seeding material is rockets. In Romania, they've got more than 1,000 people employed, but I've been told that in the UAE it's risky to shoot rockets around Dubai International. So I would say in 10 years' time, I see UAVs being the main, if not the only, means of delivering seeding agents in the UAE and probably most operational projects in the world.
Yeah, I think you're probably correct. And that indicates how hard we need to work to address those non-technical stumbling blocks that stand in the way. In the context also of the global realities where these UAVs are probably looked at with some more suspicion in certain parts of the world than 3 years ago. So I want to thank all of you for the good presentations and insightful presentations you gave and for participating in this panel. And I want to ask the audience to thank the speakers and panelists in the usual way.
Let's give our panelists a round of applause for their engaging and insightful discussion. Before we move to our next session, we will take a short coffee break and we will reconvene at 11:45.
Will Cantrell will visit this afternoon about some of our collaboration. Together, we're advancing a project titled Laboratory and Modeling Studies of Cloud Susceptibility to Hygroscopic Seeding. This initiative is critical in helping us understand the behavior of clouds at a microphysical level and how they respond to hygroscopic seeding particles. Such work is helping to shape the future of cloud seeding by enhancing our ability to target specific atmospheric conditions and maximize the effectiveness of our interventions. At the core of WMI's operations is our sister company, Ice Crystal Engineering, which has pioneered the production of ISO-certified cloud seeding pyrotechnics. Ice Crystal Engineering's materials are deployed globally, more than 20 countries, representing the cutting edge of safe, effective, and scalable cloud seeding technology. These materials are tailored to suit a variety of environments and conditions, which is essential for tackling the diverse challenges presented by cloud seeding efforts worldwide. Our work at WMI, together with leading research institutions, underscores the importance of strategic alliances in the field of weather modification. Through our robust partnerships and ongoing research, we can make significant strides in developing seeding materials that respond dynamically to specific meteorological conditions. UAE REP's grant assistance and science-based selection process are vital to this endeavor, as they empower organizations and researchers to push boundaries, test new ideas, and pioneer technologies that will serve generations to come. As we move forward today in our discussions, let us remember the transformational nature of this session, advancing our ability to optimize weather modification programs impacting millions of people worldwide. I look forward to exploring new ideas and strengthening partnerships that will help us achieve this goal. Thank you very much.
Thank you, Mr. Sweeney, for your insights into the ongoing advancements in cloud seeding methods and materials. Dear audience, as usual, we will be taking questions to our upcoming presenters during the panel discussion after all three presentations are completed. Please be sure to submit your questions using the QR code, and our moderator will address them. Our first technical presentation in this session will be given by Milosav Bilorid, a senior researcher at Korea Meteorological Administration.
So hello everyone. It's really a pleasure to be here and deliver my presentation on behalf of National Institute of Meteorological Sciences in South Korea. Let me start with a brief background of cloud seeding in South Korea. So the cloud seeding in South Korea is currently still purely experimental. We use both the glaciogenic and hygroscopic materials, and do conduct cloud seeding with aircrafts and ground-based cloud seeding technologies. Each experiment has to be evaluated individually and using assessment methods that are relying mainly on observation and numerical modeling. But recently, in 2022, we established our first cloud chamber laboratory where we can conduct cloud seeding directly in the laboratory settings and study about seeding materials and their impact on cloud microphysics. So the laboratory is still very new and is just beginning to produce scientifically valuable data. So today my goal will be to share with you some of example of our results and demonstrate how we use them in our numerical modeling approach. So the centerpiece of our laboratory is the expansion type cloud chamber. The chamber uses the adiabatic cooling process to form a cloud. So basically, once we began the evacuation of air using vacuum pumps from the chamber, with the decreasing of air pressure, we also decrease the air temperature. To eliminate the heat fluxes from the walls, we also cool down the walls of the inner chamber. So the concept is very similar to the MRI chamber or IREF chamber at KIT. And once the right conditions are met, we can observe formation of cloud droplets or ice crystals. And then we can use instrumentation such as CPI to study the hydrometeor characteristics, for example, the ice crystal typology, as you can see here on the right side. Currently, we are still validating the cloud chamber. For instance, we use the Pine chamber, which is kind of smaller version of cloud chamber. And we see a very nice agreement between these two chambers in terms of ice nucleation, which give us kind of confidence that in the reliability of our experiments. And the chamber is actually not the only important feature of the laboratory. So we also have a wind tunnel where we can burn seeding flares at various wind speeds up to 90 meters per second. And also we do have an aerosol chamber, which is kind of buffer tank where we can conduct analysis of aerosols that requires more time. Or we can use the aerosol chamber as an intersection between the wind tunnel and the cloud chamber. For the numerical modeling of our cloud seeding campaigns, we use the mesoscale model, the WRF model, and currently we are developing a new approach which is based on the fast spectral beam microphysics. And currently we are focusing only on the simulation of the experiments with hygroscopic seeding flares. So for that, we need some basic information about the aerosols. For example, the particle generation, size distributions, and the hygroscopicity. Fortunately, we can obtain this data from our laboratory experiments. So once we burn the flares inside the wind tunnel, we can measure the change in the number concentrations inside the wind tunnel using instrumentation such as CPC, and then compute variables such as the seeding rate or particle yield per flare. For the size distribution analysis, we basically inject sufficient amount of particles into the aerosol chamber and then conduct the analysis using instrumentation such as SMPS and OPC. For the hygroscopicity analysis, we use methodology that is based on the single parameter kappa value described by Peters and Kredenweiss in 2007. So basically, we use the SMPS and the DMA column to select a specific size of particles and then pass it to the CCN counter and CPC. Then we can use the ratio between the CCN and total number concentration to estimate the critical diameter by taking the center value of sigmoid function that is fitted into the data. Then we can use this critical diameter in our Cooler equations to calculate the hygroscopicity kappa parameter. In my example and also in our field campaigns, we use two models of hygroscopic flares. The first one is the Tarhuna MK1 from Cloud Seeding Technologies, and the second one is the HBIP from Ice Crystal Engineering. Both flares, they are burning place seeding flares with main agent calcium chloride. Here on the right side, you can see the results of analysis of the particle generation On the left side is for the 5 meters per second airspeed, and on the right side at the 30 meters per second airspeed. And at the top you can see results for the Tarhuna Mk1, and in the bottom the HBIP. As you can see, in all 4 cases we had very nice linear decreasing trends in the particle generation, and with very high correlation coefficients, which give us kind of confidence that we can use these linear regressions in our mesoscale modeling approach. So we can implement these regressions into the model, as in this example, where you can see the combination of aircraft-based and ground-based cloud seeding using the HBIP and Tarhuna Mk1 flare, and each of the line represents actually the generation of particles from single flare. So we believe this kind of approach is more realistic compared to the, for example, constant particle release approach. Another interesting finding was that the particle yield is very dependent on the airspeed. So with a very low airspeed, for instance, the 5 meters per second, in case of Tarhuna Mk1, we got 10 times smaller particle yield per flare, which is most likely associated with the coagulation processes which are undergoing during the combustion inside the wind tunnel. And this also agrees with our size distribution analysis. So what we see is that in both flares with a low airspeed, we got generation with greater amount of larger particles. We also compared the 2 flares each other at 2 different airspeeds, and we found that actually the HBIP from ICE company slightly seems to generate a greater amount of larger particles. When we want to implement this data into numerical model, we first take the data from the laboratory and fit it into our spectral model microphysics scheme. To fit it into our beans, we use 33 beans. They are logarithmically equidistant. And on the right side, in the center, you can see how the distribution looks like in the model. And on the right side, you can see the comparison with the background aerosol, so, which is already in the model. And so you can see that the seeding aerosol is actually significantly larger. Let me move to the hygroscopicity analysis. So before applying this method on seeding flares, we first tested on some pure chemical compounds. For instance, we use it on sodium chloride at the top and calcium chloride at the bottom, as you can see. Here are the estimated critical diameters for different supersaturations. And on the right side, you can see the corresponding hygroscopicity kappa values. And then in the table, you can see the overall hygroscopicity taken as an average of these kappa values. And we found that we have very nice agreement with the literature, which give us confidence that our instrumentation is well calibrated, and we can use it in our seeding flares analysis. So these are the results for the seeding flares, and what we found is that actually the seeding flares has much larger hygroscopicity compared to the pure calcium chloride, which was interesting because the calcium chloride has 0.7 kappa value. We got above 1 for both flares. So it appears that there is some contribution of other particles which are also very high hygroscopic and are part of the seeding material mixture. So for the further insight, we should also include one of our instruments which we did not use yet. That's the ion chromatography. We conduct same experiment also with the novel material developed here in UAE, the titanium dioxide coated sodium chloride. But instead of wind tunnel, we use here the brush aerosol generator to inject the aerosols into the aerosol chamber and then conduct the experiment. Before I show you the actual results, I would like to point out one very important limitation of this methodology, and that is the size range. So in this method, we can work with very small particles from 20 nanometers to 0.5 micrometers in diameter. So that's smaller than the most effective particle size, which is from 0.4 to 10 micrometers based on the previous studies. So please keep this limitation in mind. And here are the actual results. As you can see, we tested the material for a wide range of supersaturations from 0.2 to 0.8%. And what we found, actually, the critical diameter was quite large compared to pure NaCl, which give us overall very small hygroscopicity kappa value, 0.02. But then when we consider also the the higher surface tension, that give us 10 times greater hygroscopicity, but still not enough compared to the pure NaCl, which is 1.3. So why is that? So our hypothesis is that the titanium dioxide coating of the NaCl, despite its very good adsorption properties, it appears that it caused some kind of time delay for particles to reach its equilibrium. So in other words, these small particles will not activate immediately when exposed to the supersaturated environment. But when we look at the results from the data from the OPC of the CC encounter, we actually found that the size of the droplets that nucleated on the novel material were twice as large as the droplets that nucleated on the pure NaCl, which is in agreement with previous studies. So we really would like to study more about this material in our cloud chamber, which can give us more insight for the whole. We can use the whole spectrum in the cloud chamber. We have more residence time there. So after validation of the cloud chamber, we will definitely in near future conduct more experiments. But for now, we use again the Pine chamber, which was developed by the Bill Finger and KIT, to analyze the potential isonucleation activity of the novel material, even it is hygroscopic material. And indeed, we found that actually the titanium dioxide coating seems to cause that the material began the nucleation at higher temperatures than the pure NaCl. So it was in minus 26 degrees Celsius, while the NaCl is minus 37 degrees Celsius, which is pure homogeneous freezing of cloud droplets. So it indicates a moderate isonucleation activity. At the end of my presentation, I would like to show you some numerical modeling results, but since there is not much time for that, and also the model is still under development and undergoing many sensitivity tests based on the parameters, I would like to show just one example where we use this model for simulation of one of our the ground-based cloud seeding experiment at our high altitude station. We use here 14 hygroscopic Taruna Mk1 flares, and we use the parameters obtained from the laboratory. So here are the results for the model. These are the 3 hours after the cloud seeding in terms of precipitation, the change of the precipitation based on the difference between the seeded and no-seeded scenario. So what you have here is actually the colors represents, the red color represents the positive values, which meant to be the rain enhancement, while the blue colors, negative values, represents the rain suppression. So as you can see, we had both cases in this scenario, and we actually found that quite nice agreement with the observation by weather stations. So basically, in areas where we got, in the blue areas, we got less precipitation, and in red areas, we got more precipitation measured by the automatic weather stations. But we still need to do more evaluation and development. Another thing, we found that according to the model, the maximum rain enhancement was approximately 0.3 millimeters per hour. So these are my conclusions. I think I do not have much time to go through all the points. I would like just to give you my final thoughts, and it's, we really find this kind of laboratory to not be useful only for studying seeding materials and their impact on cloud microphysics, but also to improve our numerical modeling skills. Yes, so that's all from me, and thank you for your attention.
Thank you, Dr. Billard, for your informative presentation. Next, I invite Professor Linda Zhu, an inaugural first cycle awardee of the UAE rep during her time at Khalifa University here in the UAE.
Okay, the title page seems not there, right? Anyway, good afternoon, ladies and gentlemen. It is my pleasure to present today's presentation. I think the first title page is not showing properly, but doesn't matter. Today, I will talk about the novel cloud seeding materials and the complex interplay between the material science and cloud physics. As we know, water cycle is a continuous movement of water around the Earth, and it happens all the time. You may notice or may not notice, but it's non-stop and ongoing. So we have, water cycle is driven by several processes. So one of the process is evaporation. So the water are evaporated from mostly ocean body and become airborne vapor. The processes of condensation and precipitation are closely related to the rain formation. Other processes include sublimation, infiltration, surface runoff, and underground subsurface flow, such as groundwater. It is important to know multiple factors affecting the rain formation or precipitation formation in the water cycle. So the pretty important one is the availability of water vapor in the atmosphere. So we need to have them and have a lot of them. These vapors, water vapor, are mobile. They can move left, right, up and down. The second factor will be mountain terrain, such as hills, high mountains. They act as a barrier for the water vapor. So when the water vapor air mass heat the mountain, what happens? They move up and increase the humidity and has a chance for the condensation. Vegetation is another factor, such as tree leaves and grass. They absorb CO2 and release water vapor. So this biological process is named transpiration. It is also contributing to the water vapor in the atmosphere. Volcanoes, wild bush or forest fires all generate fine particles and in the form of ashes or smoke. So these fine particles can be acted as condensation nuclei. So they are critical to form the precipitation. Water exists in 3 different states: liquid, solid, and gas. So the conversion from one state to the other can be achieved by the phase changes. For example, the condensation is one of such phase changes. It changes from air and into liquid water. What actually happens is the water vapor combine with the tiny particles and form small, very tiny cloud droplets. And these nuclear materials, where they come from? Most of them in the open atmosphere comes from natural processes, such as volcano eruptions, pollens from the plants, and sea salt crystals. You know, the water, the air, the wind blow the ocean waves and generate sea spray. So when the water evaporated from sea spray, what's left? Salt crystals. And those salt crystals will be blown as, in the atmosphere as seeding nucleus. Of course, fine dust particles. So in the atmosphere, only one multiple above-mentioned factors coexist in the same spot. Then there will be a chance to form rain. So in a way, rain formation is a random event subject to probability. And the probability of rainfall varies in different regions of the globe. In some regions, high. In some regions, such as arid desert regions, the probability of rainfall is low. And the question we ask here is, can we make an effort to increase the probability of rainfall? Artificial seeding agents against those biological processes. So artificial seeding is one of such effort. It can be designed, fabricated, from understanding of what will happen, and most importantly, they can be deployed or spread, released with informed decision. I think this part still need a little bit more information on that. So all aims to increase the chance of rain formation. In the UAE first cycle call for proposals, they funded my project. The title is Using Nanotechnology. The key word here is nanotechnology. It's not about simple mix of TiO2 and salt. That's will causing problem. It's about precision, nano thickness, and nano size. So you have achieved the balance, not compromise the hygroscopic nature of the salt. So the title is Develop Cloud Seeding Materials for Accelerated Condensation and Rain Formation. The research motivation and hypothesis is particles' ability for rain enhancement could be affected by the interfacial interactions between the particles and the vapor in the atmosphere. So here we are not treating salt, the seeding agents as an abstract particle. Instead, we zoom into the details, look at its chemistry on the surface, such as hydrophilicity, size, and porosity. Those terms are familiar for the material science, but a little bit new here for the atmospheric physics, but they do matter. So factors such as this play a role in its efficient in cloud formation and seeding. Another motivation is to find alternative materials, trying to avoid silver iodine, because mostly it is for cold cloud seeding. So one, NCM is more interested in warm cloud seeding, so I need to find something different. And second, as earlier presenter mentioned, long-term the use of silver iodine could have some implications in health effects to marine life. So the formation of precipitation in the warm cloud scenario, so we can see the nuclei really initiate the condensation, and then causing the droplets growth through collision, coalescence, until the water droplets are big enough, they fall. So the key word here is we need large water droplets. So if the condensation already formed larger droplets, so it is acceleration, it is a shortcut. To conversion from gas to liquid water, it requires to overcome this Gibbs free energy, delta G. And the delta G is intrinsically related to the surface hydrophilicity. That means how they act with water. Also, the surface hydrophilicity is described by a parameter called the water contact angle. In the cold cloud seeding scenarios. We can see with the presence of the ice nucleating material. So the water can be frozen at much warmer temperature and at less supersaturation degree. So this means the probability is increased, so it makes it a little bit easier. If we look at the graph on the top right corner, it is a material has a water contact angle 180 degree. That means this material is hydrophobic. It doesn't like water. So the corresponding Gibbs free energy is very high. So if we reduce the water contact angle to the bottom, and that material has a water contact angle 0 degree. So the corresponding Gibbs free energy is so low, it's almost 0. That means they will be like water, can attract water. So based on this type of background information, so in this first cycle project, we've designed, synthesized novel cloud seeding material using nanotechnology approach. So one is core shell microstructured material for hygroscopic cloud seeding to form larger droplets. And second is porous composite for ice nucleating glycogenic seeding to initiate ice and go as crystals. So for the core shell microstructured material based on the concept to promote the synergistic effects, combined effects between the hydrophilic shell and the hygroscopic core. But the concept is the shell and core, there is a thickness difference, 200 times, for example. You can't make it 1-to-1, that's too much of the shell. It's a reason called shell is very thin, all right? Okay, so because of TiO2 is a shell, they are nano size and they have a lot of hydroxyl groups and make them a hydrophilic material. So they are responsible to attract water molecules and make the local moisture much higher and causing some partial dissolution of the hygroscopic core, which is a majority of the material, right? And this causing a vapor pressure gradients. When you have these gradients, so the process can be sustained. So vapor will be accumulated until the material turning into a larger water droplets, as illustrated the yellow and the up one. So we examined this concept by real-time observation by the environmental SEM. So environmental SEM is equipment which can control the moisture and temperature. So the first column, you can see they are the two materials, salt only and core shell structured particle, when they are in the crystal form, in the size as well, without the experiments. So at the end of the last column, they are all turned into droplets, and we can see the difference in the droplets. So for the NaCl only, they turn into droplets but a similar size. Okay, so we can see salt can be a useful cloud seeding material, but will that make a shortcut, make it more efficient? Not as much as the core shell, which when they turning into droplets, their size increased 7 times in these experiments. It will be different if in the different. So now we can observe through video about this change. The left is a NaCl, the right is a core shell structured. So you can see the core shell is activated at much lower relative humidity, and when they finish, they form a much larger water droplets. But the key thing is the titanium dioxide is nanometer thickness. So both materials are further evaluated by the cloud chamber. Cloud chamber, as a few people talk about them here, it is a small room with controlled temperature and humidity. And also, cloud chamber is equipped with an electronic camera and with aerosol spectrum counter. So after the seeding material is released from the top of the chamber, then we will start collecting data. After 5 minutes, so we can see the B, the image. In the core shell structured experiments, we found the droplets are formed larger in size. So we found a larger droplet size as we found in the SEM. And the next questions, we know it's larger. How about the quantity? Is this larger molecule more of them or just a few? So the next question can be answered by the aerosol spectral counter. So you can see the highlighted one is in the large size spectrum, which is 10 to 25 micrometer. They are the size range is more likely to form rain. So we can see the blue one represent the core shell structure, and the red is the normal salt. There is a 3 times bigger droplets formed by the core shell structured material. So they prove in 2 experiments, they turn into larger droplets. Remember I said in the coalescence process, its end game is larger droplets. Here already form larger droplets. So it has potential to be further utilized. So the next material is porous composite for ice nucleating. So the concept of this material is based on using 2 materials. One is a graphene oxide, which provides a template for ice crystal growth. And because they have a similar hexagonal lattice structure for ice growth. This is borrowed from the concept of silver iodide. Okay. And second is silica oxide. It's fine sand particles. So silica oxide nanoparticles, they are hydrophilic as titanium dioxide, and they also prevent a role to reduce the restacking and the aggregation of sheet RGO. And both of these material be prepared into a 3D sponge porous material. So they are sponge-like. You can imagine this is a tiny sponge. So this material provides roughness and porosity, or cavity. Porosity is another word, is cavity. These cavities are quite important because the water will fill into the cavity, and then the water inside the cavity temperature reduce and relative humidity increase and can initiate ice nucleation. The enough water in the cavity can grow into ice crystals. This is confirmed by this SEM observation. 2 areas of this porous material. So left side is a smooth area. The right side is a hole, is a cavity. It's a very small cavity, but we're using SEM. So you can see in both situations, they form ice. In the less roughness area, they form a layer of bulk ice because of the competition of the water moisture. On the cavity side, they form crystals, hexagonal crystals. Yeah, I like to mention, without the nucleating materials, the water will only be frozen and much lower temperature, such like minus 36 degrees or even lower. But with this porous ice nucleating material, and it can be formed at minus 8, and with very low relative supersaturation, like 5 to 8%. This is still experimental observation. It can subject to variation, could be even better in the larger scale experiments, right? So we can see different ice formation patterns as well. In the cavity, they form ice crystals because there's enough supply of water vapor. In the less rough areas, they form layer of ice. Okay, I'd like to draw some conclusion by employing the advanced nanotechnology approach. By the way, apart from this, I'm using nanomaterials preparing membranes for desalination and membrane for catalytic water reuse and recycling, so this is my comfortable area, right? So using advanced nanotechnology approach aims to enhance the interactions between the interfacial of the nuclear particles with the water vapor. It do matters. We look at them. And so with the nanometer scale precision and the thickness and size, so we prepared two materials. One is core shelled material, which provides synergistic hydrophilic shell and hygroscopic core, turning into a large water droplets. And the second is porous composite material, which can initiate ice nucleation at a warmer temperature and promote fast ice growth. Before I talk about outlook, I want to share this photo. This photo was taken by myself 2 weeks ago at 4 p.m. on 3rd of January in Abu Dhabi, close to where I live and close to here, right? And on that day, you can see a very thick, dark cloud gathered in the sky of the Abu Dhabi. Normally, this type of cloud, I guess, should lead into a steady, medium, or heavy rain. But on that day, let me tell you, they end up dissipated very fast, end up with a very light drizzle. And disappointed a bit, but yeah, maybe the weather data can tell a little bit more on this, why. Okay, let's talk about the outlook. Investigate the relationship, the dose cost effects, and of how much, and also revisiting the operational delivering protocol, focus on where, when, what, how, those type of questions, which is some people already presented very good initiatives today. Also scale up the fabrication, particularly focus on the quality and cost. Expand to other applications, such as smoke fog reduction for pollution control, which is an issue for some countries, and hailstorm suppressions, and hydroelectricity generation, if for the regions you can cause seeding quite a lot of rainfall. Thank you. That's my presentation.
Thank you, Professor Zhu, for your comprehensive insights into the novel cloud seeding material. Our final presentation in this session will be delivered by Otmar Mohler, Deputy Director at the Institute of Meteorology and Climate Research in Karlsruhe Institute of Technology.
Thank you, Hamda Alosani, for the introduction, and it's my pleasure to be in this fascinating environment and to participate in this inspiring rain enhancement forum. And I would like to thank the organizers and the IREF in particular for inviting me and giving me the opportunity to talk about our work at the Karlsruhe Institute of Technology, which is centered around what I call expansion cloud simulation chambers. So I also would like to start with a short introduction, and I think you all know that aerosols have two particular important roles in cloud formation. The first is they act as cloud condensation nuclei, and for that process, most of the particles, or a large number fraction of the particles, typically contributes to that process. And the second role is the ice nucleating particle role. This is forming primary ice in clouds, and by that also initiating the processes that lead to precipitation formation. And in this process, only a very minor fraction of all the particles participate, and that's why it's so much more difficult to quantify and understand these processes, and also to predict and formulate those in models to know better and do better kind of job of predicting primary ice formation and related precipitation formation processes. And in particular for ice formation, I talk a bit more about ice formation, but also a little bit about more recent studies we did for cloud condensation in our chambers. So I would like to focus on immersion freezing in mixed phase clouds, where the particles have to be immersed in supercooled liquid droplets to act as ice nucleating particles, and to make this minor fraction of droplets freeze, which would then grow in expanse of the supercooled liquid phase to form larger precipitating droplets or particles. So we are using, just before I introduce you to our chambers in Karlsruhe, I would like to very briefly go through the basic principles of a cloud simulation chamber, expansion type cloud simulation chamber. So it's basically simulating what happens in updraft in the atmosphere when air parcels are rising. They experience decreasing pressure due to the barometric height formula. That means they expand and are cooled according to the adiabatic equation. So we are lowering the temperature, and by that we're also lowering the saturation pressure. And by that, relative humidity is increasing. And so these processes we can simulate in our cloud simulation chambers just by pumping, starting from constant pressure and temperature conditions, as you see in this graph. So the upper panel shows you the pressure curve, and the next one the temperature, and the next one the increase of relative humidity with respect to a supercooled liquid phase and the ice phase. So this experiment was just started at a temperature around minus 20 degrees centigrade. And this is similar to what Miroslav showed you already for his CPAC chamber in Korea. So same principle. And in the lower panel you see the result of an optical particle counter that measures the number of aerosol particles first before cloud forms on the left side, and then you see this dense area of cloud droplets forming, very narrowly distributed in the size range. Those are the droplets, and only very few of them are freezing because we seed the cloud in this case, also with some ice nucleating particles, and only a minor fraction of dots you see above the liquid cloud in the lowest panel here, which are the ice crystals that formed by the action of these minor fraction of ice nucleating particles in our aerosol. So it's a seeded cloud experiment, so to say, where most of the aerosol particles acted as CCN and only a very minor fraction acted as ice nucleating particles, which we can then quantify and understand as a function of the temperature, the cooling rate, and the type of aerosol and other factors or parameters. So a very controlled experiment, and we are operating a number of expansion type cloud simulation chambers at KIT. So the left one is the biggest we are operating since more than 25 years. This is actually now replaced by a new one we developed in the framework of an ACTRIS project, so funded by our Ministry of Research. So we are demolishing that or refurbishing that with a new one which we build in the next 2 years. The second from the left is a smaller one. We call it Dynamic Cloud Simulation Chamber. I'll tell a bit more about that in a minute. And then we also developed mobile chambers which have only a 10-liter volume. So the left one has a volume of 84 cubic meter, and the smaller ones in the middle part of that page are mobile systems which have only a 10-liter cloud volume, which can measure ice nucleation in ambient aerosol, but also in the laboratory. And Miroslav showed some applications of this instrument, which is called PINE, Portable Ice Nucleation Experiment in the laboratory, but it can also be applied in the field to measure in a field site the abundance of ice nucleating particles. And the second one is a more recent development. We also want to bring that instrument to an aircraft, an aviation-based system, so to say, which we call PINE Air, measuring the same thing, but then mobile in the free troposphere and in the place where research aircraft can operate. On the right side, you just see two photographs, the upper one from the big AIDA sea chamber and the lower one from that new dynamic cloud simulation chamber. Okay, so talk a bit more about this new dynamic cloud simulation chamber that just came into operation. It's a completely innovative new design of a chamber inspired by similar chambers which were operated at the Colorado State University or at MRI. Masataka is here. He is operating such a chamber also at MRI. And this is where the cloud chamber sits in the vacuum chamber. The vacuum chamber makes the pressure difference, or pressure reduction. The cloud chamber has coolable walls. So we can cool the walls of that cloud chamber at well-controlled rates up to 10 Kelvin per minute. And by that, apply cooling to the walls of the chamber at the same rate as the cooling of the expanding gas inside. So we can perform isothermal expansion type cloud simulation experiments in this facility, and that goes down to a temperature of minus 55. And we can also do warm cloud experiments in this facility, and then we just add air with a certain moisture content, so we also have a control of the liquid condensation level in this cloud. So we can really study also CCN processes at low cloud base temperatures, so to say, or liquid condensation temperatures in this facility. And this just show you an example of the control of temperature change. So on the right side, you see 3 experiments performed at 1 degree centigrade per minute cooling, and 4, and then 10. So the one experiment with 1 degree centigrade of cooling per minute is about an hour. So we cooled from plus 10 to minus 50 degrees centigrade. So that is a 1 hour experiment. And of course, the 10 degrees centigrade per minute cooling experiment only lasts 6 minutes. And you see how well the temperatures, those are signals from different temperatures throughout the chamber, are very well aligned around a mean. The control is better than plus minus typically 1 or so degrees centigrade, depending on the cooling rate. Okay, sorry for the busy graphs here, but just to give you an idea how the data looks like. So Miloslav showed a similar graph actually. So you see from top to bottom temperature, pressure change, temperature change, and the result of this optical particle counter for the cloud droplets and ice crystals that were formed in the experiment. And please look at the arrows. So just on the left side, this is an experiment which is called clean conditions. So the number concentration of aerosols was only 230 per cubic centimeter. And in that, so the lower arrow is pointing to the 4th panel, where you see in the black line the number concentration of the particles, and in the reddish line, you see the droplet number concentration. This is an aerosol-limited case where the droplet number did equal the number of aerosol particles. On the right side, we had a polluted case experiment where the number concentration of aerosol was about 8,000 per cubic centimeter. And in this case, you see in the lower pointing arrow that now the number of droplets is much smaller than the number of aerosol particles. Now the number of droplets more depends on this dynamic role in CCN activation. And this is what we want to study, because if you add a certain second mode of particle, and this was the topic of a recent series of experiments we did, also by modeling or theory, you may expect, depending on the activity of the second mode of particles you add, and the left graph shows that. So on the vertical scale, you see the droplet number, and on the right, the number concentration of extra particles added to the system. You see eventually, depending on the relative activation thresholds or critical supersaturations, these different types or modes of aerosol particles need for activation, you may even see a decrease of number of cloud droplets. And this is, we want to study in more detail, and also then understand with the help of high-resolution modeling for our cloud simulation chamber in the next time. So we already have a number of results, but I'm not able yet to show you the results. We're still analyzing the data here and compare that to the modeling results as well. So then, very shortly, the introduction to the PINE facility. This is this mobile cloud simulation chamber. It has, on the left side, you see it's also composed of a 10-liter cloud chamber sitting in a cold environment, so to say, so we can control the temperature here. We can then, in a first step, you see a series of operation. Now, this is the time scale here of this series is, I think, 30 minutes. So every 6 or so minutes, we do an expansion. After we have sampled or collected some ambient aerosol or lab-generated aerosol into the chamber, we do the same as in the big chambers. We lower the pressure, we activate the collected aerosol as CCN. You see in the lower panel this dense cloud of droplets, and then only a few of them are freezing above. Those are these dots at larger optical diameter, which we then can quantify, and by that measure every single run every 6 minutes or so, the number concentration of ice-nucleating particles, which equals the number concentration of ice crystals we measure in the experiment. And this is an automated system which can run 24/7. So you just bring it to a site, plug it to electricity. After an hour, it starts operating without much operator attendance. A student can be trained within a day to operate that, also remotely from home. And this is 1 year record of measurement with such an instrument at a mountain station in Austria. And you see an annual cycle at that mountain station, and also some diurnal or daily changes. The highest peak in the middle of the graph was a Saharan dust storm that came along across Europe, where the dust number concentration was increasing, and by that also the ice-nucleating particle concentration. So dust is a very important immersion freezing nucleus, probably also here in the environment in the Emirates. And this is just a map showing the locations where this instrument, so it's commercially available, was already operated for a longer time period. We are at the moment just preparing a paper to compare what we measure also to global modeling in collaboration with the University of Leeds and the GLOMAC model. So just to constrain also the model in predicting, formulating, calculating a number of IMPs and also rates of primary ice formation in modeling with what we measure over longer term in different places around the world. And eventually sometime soon would be great to have such an instrument also operating here in the Emirates to monitor the environment here for ambient or natural ice-nucleating particles, which provide a basis for the clouds to form and develop their precipitation before they are seeded to maybe change their behavior in precipitation patterns. So I do not have much time, so already mentioned we are developing this aircraft-based system we call Pioneer, probably being flying for the first time on the German Halo aircraft in the Southern Ocean environment this fall already. And just come to my summary and outlook. So hygroscopic seeding, I think we can study this competitive effect of different modes of particles with different critical supersaturations very well in our dynamic cloud simulation chamber. That's what we do more in the future also. And then glaciogenic seeding, I think we can do both in the cloud simulation chambers, but also using the PINE instrument. And both in the lab and also in the field to get a better idea about ice nucleation activity of particular aerosol types and also about ambient abundance and variability of ice nucleating particles in environments where clouds form and seeding activities may be planned and happen. And for new seed materials, so this is just one graph. We did an inner comparison like Miloslav showed with the different techniques. So we used SNOMAX here, so these bacterial strains which were developing ice nucleation activity around -7 to -9 degrees centigrade. On the right panel in a very steep curve, so to say, very narrow temperature range where a fraction of those are activated. And you see the nice correspondence of our different techniques of measuring ice nucleation activity or ice nucleating particle. And I think that can be also used more in the future to characterize not only ambient aerosol types, natural aerosol types, but also seed materials, both in larger lab-based facilities or cloud simulation chambers, but this PINE instrument could also moved or operated in seed material facilities or test facilities to characterize very quickly with less efforts than with a big cloud simulation chamber the ice nucleating properties of such new seed materials. Okay, but overall, I think it's not only about seed materials and new seed materials, it's also about the operational aspects. That was discussed more in the first session this morning. So it's equally, if not even more important in my mind, to talk not only about seed materials or new materials for seeding, glaciogenic seeding in particular, but also to have in mind optimized seeding operations. So where, when, and how much to seed. And in particular for ice seeding, probably one may need less material, but the question is how has it to be distributed in a more widespread way or in a more local way, in updrafts, below the clouds or inside the clouds. I think those are questions which are equally important than the work on the properties of these seed materials. And I think also in the long-term run, it would also be important to study these natural seed materials for clouds, to know about the natural abundance of aerosols, CCN and IMPs in the environment where cloud formation occurs and seed operational activities would be planned and happen. So I think that is also an important aspect that needs to be known as a basis for cloud seeding, so to say, and cloud formation and precipitation formation. I thank you very much for your attention.
Thank you, Dr. Moller, for your enlightening presentation. We now move to the panel discussion, where our experts will take a deeper dive on the latest advancements and opportunities in the development of new cloud seeding materials. Please join me in re-welcoming our three presenters, joined by Professor Will Cantrell, a UAE-REF's fifth cycle awardee and Associate Provost at Michigan Tech University, and the session moderator, Dr. Mohammed Mahmoud, CEO and founder of the Climate and Water Initiative.
fortunate or unfortunate slot of being just ahead of lunch. So either you'll be hyper-focused or not so much, but we'll make sure this is a very exciting and engaging discussion. Just again, as a reminder, questions are available for submission. So if you can follow the instructions on the screen, if you want to ask your own questions, they'll pop up for me, and I'll try to incorporate them in our already established discussion. So welcome back all, and Will, welcome again on the stage. Start with a few sort of introductory questions, and Miloslav, I'll start with you. And this is in regard to the KCPEC laboratory, and we understand how it's been instrumental in terms of understanding or moving forward our understanding of cloud seeding materials. But on that line of thinking, can you help to elaborate more on how controlled laboratory experiments at that particular laboratory has helped to translate into the real world, or translate actually more into real world cloud seeding applications, with the work that's been done in the laboratory?
Yeah, thank you for the question. So my point of view is that usually during the real-world cloud seeding campaigns, what we do, we look at the observation, surface observation, radars, data. That's the empirical data. And we try to conclude whether the precipitation was contributed by also seeding efforts. But what we, in an ideal case, what we would like to do, we would like to, for example, repeat the same experiment, but with the same condition, but that's not possible because the real world, it never repeats, right? So the conditions are still different. So we can address this issue by, for example, using the numerical model simulations. So in numerical model simulations, you can repeat the same scenario with same conditions. What you can do, so you can do one scenario with the cloud seeding, one without cloud seeding, and you can compare. But in field campaign, you cannot do that. But the issue with the numerical modeling is that it's not the empirical data, it's the theoretical data, which suffers like uncertainties and inaccuracies. But at the third place, we have this kind of laboratories where you can with precise instrumentation, you can obtain empirical data and also repeat the same conditions. So that's very important, for example, for development of new seeding materials. So simply put, you can set your experiment, you can inject aerosol in the cloud chamber, you can conduct the experiment, and then repeat the same experiment, but for example, using just ambient aerosol and see what are the differences and conclude that whether the seeding was effective or not. And that's one aspect, and I think there is also another aspect, and that is what I was also talking about in my presentation, and that's the importance for the numerical modeling. So we can use the data from this kind of laboratories to initialize the numerical models. I think yesterday in the last session, I think Daniel, he pointed out the importance of aerosol information for numerical modeling simulations. So this data we can obtain from these laboratories. And for the real world application, real world simulation, seeding experiments, we can use this numerical model to predict the outcome of the seeding before conducting the cloud seeding. So it's very important for decision making as well. That's my point of view.
Excellent, thank you. Thank you for explaining that. Linda, next question's for you. And I think one of the takeaways, many takeaways from your presentation, but one of them is the idea that nanotechnology has really been a revolutionary sort of force in many fields, obviously including cloud seeding. Could you just explain or maybe discuss a little bit more on the unique properties of the nanomaterials you've particularly developed under your experiments and how they've addressed some of the traditional limits on conventional seeding agents?
Thank you for the question. As I briefly mentioned in the presentation, so I see the most important contribution of this project and this approach is not accepting any particles as it is. Instead, we look into details and aims to, can we artificially, using nanotechnology, to fabricate, to synthesize based on a designed concept. So aims this material can exceed or open up a gate of more possibilities in more efficient cloud seeding. It doesn't mean the material I presented will be the end products or will be the best. Too far away from that. But at least they open up this door of this approach, which instead of accepting whatever particle we have as the same, a physical object, so now we zoom into it, it's not only a physical object, it has chemical properties, and we can manipulate that.
Excellent, thank you. We'll just go down the line as we are. So full disclosure, before I ask this question, I am a former graduate of Michigan Tech University, so I may have some bias a little bit on some of the work that you're doing as it regards to the pi chamber at Michigan Tech, which I think is really a great tool in terms of some of the experiments that can be done. And of course, allowing for the use of controlled substances in a way, or experiments, I should say, in a way that is very informative for some of the research that we talk about here. Could you elaborate and discuss a little bit more and describe some of the key findings from your particular studies on cloud susceptibility to hydroscopic seeding?
I'll start with one of the issues that we've run into that we weren't really expecting at first, and that was the issue of dispersal. So if you have a flare, that's your dispersal mechanism, because it burns and it generates the particles, and that's pretty easy to collect and then to generate, to inject into your chamber. But if you wanted to use something like quartz shell material, you can't generate that by burning. And you can't generate it by atomization. You have to disperse it as a powder. And it tends to be very hygroscopic, and so it will clump together. So how do you get that into a situation where you can disperse it easily as a powder, even in a volume as relatively as small as the one we have, much less over, cubic kilometers like what you would see in a cloud? I think we've surmounted that difficulty. In fact, when I leave here tomorrow morning, early Friday morning, and go back home, I'm stepping into the middle of a series of intensive experiments that we have planned coming up in February. So we'll see then whether we have surmounted that problem successfully or not. One other point I'll add is one of our key findings has been in looking at the size dependence of the shape of the cloud droplet number distribution based on what you put into the cloud. In other words, based on the aerosol that you put into the cloud. We know a lot about how the number of cloud droplets depends on the number of aerosol particles. But we don't know as much about how the aerosol particle number distribution leads directly to the cloud droplet number distribution. And what we found is it doesn't matter much at all. So if you have the same number of 50 nanometer particles or 250 nanometer particles, the cloud droplet size distribution doesn't seem to care. It's the same. Wow. But stay tuned. We'll have more in a few weeks.
That's an interesting finding, right? I think that's it's a value add in of itself, knowing that piece of information. Otmar, question for you. The PINE instrument offers a portable solution for studying ice nucleating particles, as we've understood. How do you envision its application in field campaigns? And what advantages do you see it bringing compared to traditional approaches?
What was the last question? So
the last question is, what advantages does it bring compared to traditional approaches from your perspective.
Yeah, I think the point chamber has several advantages in some applications. So first of all, it's easy to use, so it can be really operated without much operator attendance. And students or technicians can be trained, or also scientists, very quickly to operate it. It's also automated, so it can be operated 24/7 and under remote control, so it can be placed somewhere. For field applications now, I showed that 1 year record, for instance, that was operated by a student in Karlsruhe. The instrument was sitting on a mountaintop station, and only several times in the year, maybe 5 or 6 times, a technician had to get there when power cut was happening or something. It's not yet robust for that, for instance, but we are working on making it also robust for power cut restart, so to say. And the second advantage is can not only be operated in the field, it can also be used in the lab or in facilities to quickly measure, get a first idea of ice-nucleating activity or fraction of particles, either generated ones or redispersed natural ones in the lab. And it also has a high time resolution. This is one advantage for the field application again, and a wide temperature range to measure ice-nucleating activity. But of course it has limitations. It's just a measure what's there. So you sample aerosol, measure in an expansion run how much ice forms and relate that to the number of ice-nucleating particles. So it has its strength in both lab and field sites, but also its limitations, of course. And I think what we don't know so much is, maybe not sure how much that is related to weather modification activities or cloud seeding. We do not know almost nothing about, or much less about, ice-nucleating particle concentration abundance in the free troposphere. So this development of the aircraft-based version could help to get a better idea of that, or in some future, if there's also a need or a way to monitor not only natural clouds, but also seeded aerosol, so to say, with such an instrument on an airplane. That could be also an opportunity to do, so that you get an idea about the distribution of ice-nucleating particles, primary ice-nucleation particles, so to say, in the environment around clouds, below clouds, or even inside clouds.
Great, excellent, thank you. Come back to you. We'll do another round, and then we'll if we hopefully have time, tackle some of these audience questions. So in your presentation, you mentioned simulating field experiments using the WRF model. And what are some of the critical uncertainties in these simulations, and how do you address them as part of your work?
So in terms of cloud seeding, I think, so the model, what we are now, the approach what we are developing is based on this fast spectral beam microphysics, and that's based on the droplet nucleation is based on the cooler theory. For that, important part is, of course, the information about the aerosol, but I think the very crucial thing is the prediction of the supersaturation, and that's what we see, that many times the model fails to predict, for example, cloud formation because there is no supersaturation in the model. So we need to address this issue, and one of the ways I think what we would like to go, the direction is to use ensemble models. So for example, so the ensemble models, you can basically run several models with different scenarios based on different initial conditions, which is very large source of uncertainty, or different physics. So the WRF model is well known to be very user-friendly model, and it has a lot of schemes and opportunities to change the parameters, test different approaches, and it's kind of toy, I would say, for scientists. So it's really a very helpful but powerful tool. But so we can create ensembles based on the initial condition, based on the physical approach, and then we can produce kind of either the probabilistic forecast or deterministic forecast from the ensembles to address the uncertainties and improve the accuracy of the models. But of course there is this caveat, and that's the computer you need good computer sources, so you need to run it on supercomputers, right? So, and not all institute, all country has powerful supercomputers. Luckily, in KMA we do have, so we can create an ensemble forecast. But if for those who don't have this opportunity, the only way is to try to optimize the model somehow. So using the single model approach, yeah, that's the only way. But it's like endless work. Yeah, you know, it's really not easy task.
Yeah, absolutely, absolutely. Linda?
Yes.
How do your glaciogenic and hydroscopic nanomaterials compare in terms of effectiveness and application in diverse atmospheric conditions?
Yeah, okay. So your question is about glaciogenic, right, for ice, right? Only. Okay. For ice, mostly the other part of the world, everywhere, they're using silver iodine or CO2. So both has some potential issues. Silver iodide, it's probably based on lattice matching. They probably have the similar lattice structure with ice crystals. However, silver iodide has a reputation, prolonged use, it may poison the marine lives. Maybe in the future, they will be affecting human health as well. So they are maybe not on the ideal list of cloud-seeding materials, that's why. What is your other question?
Oh, it was on just, I think you've answered in the sense that how do they compare both glaciogenic and different atmospheric conditions?
Yes.
In terms of
so the silver iodide is used as a given, and they probably, other material used is not silver iodide, it's a bacteria-based, it's a bio-glaciogenic agent. So this material mostly used for commercial ski snow generation, and they quite expensive to produce, and maybe not suitable for cloud seeding type of operation, which you need a lot of them. So I think for this bio-inspired type of biomimetic material which I'm working, maybe can bring down the cost and make it closer to open larger scale application from niche bacteria generated, like for example, pseudo, you know, those type of bacteria. It's difficult to handle and very expensive. They were controlled by several companies. Yeah, so this is a chance can massively produce into inorganic materials, but they functioning similar to the biomaterial. So that is why nanotechnology may have new tools to expand what we are already working. But I understand the key thing is to have an open mind. So when the new things come, it will bring new information and new chance for improvement and progression. But it needs more continued validation. And my other thing is this good efficiency has been demonstrated in my limited experiments. They form large droplets and very good ice nucleation as well. However, the best results will be finding the delivery method and protocols to harvesting this added advantage, because they bring a new, more probabilities in the ice nucleation and everything. So we should be able to harvesting that, and this need open mind and flexibility to revisiting what do we do, to visiting even what condition we can apply, because it's not necessarily the same condition. We may slightly different, or maybe completely different, or maybe the same, but we need to do that. So in that case, this parallelly developed, more efficient material can deliver its fate, which is result the most targeted, most efficient cloud seeding.
Yeah. No, I agree. I think it underlines this, what we've been sort of hearing is there's some level of flexibility and room in terms of material, method that are based on conditions, you know, warm, cool, etc., without even now considering cost and economic factors. So the field is wide open in terms of the possibility of navigating that in different ways, absolutely. Will, a question for you is on sort of how you conduct your work and how your research really combines and integrates the experimental aspect of your work with modeling approaches. And how does this combination of those two sides help to enhance the reliability and the scalability of your work, your findings, for operational cloud seeding? From your experience, how has that sort of come together?
I'll start with just a brief overview of how we do that. In our chamber, which has a volume of 3.14 cubic meters, so we have to call it the pi chamber. We have a model of our chamber. So we took a large eddy simulation model, which typically has grid cells of a few hundred meters, and we shrank it down to our chamber. So our grid cells are 6 centimeters or 3 centimeters on a side. So we can represent processes in the model that you would never see in the atmosphere, and then we can compare that to what we see in the model or in what we see in our chamber. So we can do a much more faithful comparison of what we see in the model to what we see in the chamber. But there are also things in our chamber that we cannot measure. We know they're there. So for example, supersaturation. I've spent my entire working life as a scientist chasing supersaturation, trying to understand it and trying to measure it. And we can do it in the model very easily. We can't do it very well in the chamber. So the model helps us to interpret the results from the chamber because there are simply things that we can do in the model that we can't do in the chamber, and also vice versa. So that synergy, having the experiments and the model talk to each other in a way that you can compare in a very robust way, has helped us to refine our modeling capability, but also our experimental capability. So if we look further out from that chain, so down the line to how does it improve operational research, the way that it really, I think, contributes to that is if you start developing things that you can trust because you've seen it, and you've seen it in a robust, reproducible way, now you can be more confident that when you put that into an operational context, that you're actually doing something that makes a difference, that actually is doing what you say or what you think that it's doing.
Yeah. It seems like the sound approach, absolutely. Last of our formal questions for you, Otmar, and hopefully if we have time, we'll hit some of these audience questions. Can you comment on the role of primary ice formation or ice nucleating particles in general, and some aspects of that that you would consider important for glaciogenic seeding with either existing or newly manufactured seed materials?
Yeah, I think what I also tried to show at the beginning of my talk, and we all know that over continents, in many cases, precipitation is initiated by primary ice formation. But what we don't know, and also not at all an expert of that in real clouds, is how susceptible or how sensitive are clouds to the amount of ice nucleating particles that induce these. They are needed to induce primary ice formation, but does it make a matter to have 10 times more, 10 times less of INPs in a cloud to make the same amount of precipitation? We just don't know, I think, yet. And before we don't know that, with all these secondary processes that start after primary ice is formed in the cloud, all this chain of mechanisms and processes that leads then finally to the formation of precipitation, it's very difficult, of course, to do glaciogenic seeding in a controlled way. But I think the amount of INPs has to be limited in a way. We know that from our experiments when we do such an expansion type experiment in our cloud simulation chamber, when we have too much INPs, ice nucleating aerosol in the system, and we get cloud formation at -20 or so, we do not even see much of the droplets. They immediately, all of them are freezing, so to say. So you can really make a cloud of too many ice crystals, and then what happens? They cannot grow in expense of supercooled liquid. It's just no supercooled liquid there anymore. So the secondary processes are even hindered or blocked in that way if you do overseeding with INPs. This is very critical, and I don't know how to go forward. And for the materials, if I have just one more minute to say, the optimized, I think ice is its own best ice nucleus. So for me, the optimal seed material would be just an ice. particle. And I like Linda's idea with these micro or nano-fabricated porous materials. But what if it would be possible to not just let them fill their pores with water and ice in the cloud, just before you disperse them, fill the pores with ice and then disperse them? That would be the best seed material, I think, for glaciogenic seeding. If you could disperse that in a controlled way, at very low number concentration, a controlled lower, higher number concentration in a widespread area with many locations to disperse, maybe that could be a good way. This is just a dream or maybe an idea, but if that was possible to disperse porous materials which have less weight, high number concentrations, and are already filled their pores with ice, that could be ideal agents for glaciogenic seeding in my mind.
You've sort of touched on a sort of quick rapid fire question I wanted to ask you all as we're winding down, and feel free to repeat the same answer differently if you'd like, or add a different one, Otmar. So very quickly, rapid fire, just in a sentence or a couple of sentences. Looking ahead, we've had this discussion through your presentations. What do you all think is the most critical breakthrough needed in the development or deployment of novel cloud seeding materials to ensure their widespread use, sustainable adoption for the benefit of weather modification and cloud seeding? We'll start and just very briefly, very quickly.
Yeah. I think that important is to have tools to evaluate the effect of the materials, and my personal opinion is I think Linda already mentioned some materials that are more ecologically friendly, so we should focus on that pathway. Yeah.
Great. Linda?
Yes. Okay, at one hand, we have nanotechnology or other technology, AI-assisted, for example, new materials, much potentially more efficient. On the other hand, we rigorously revisiting all the procedures, including the practice and the equipment monitoring, etc., to confirm the cause effects, relationships of all sorts of materials, and in a way we establish a more interconnected procedure for cloud seeding. So in that way, the feedback is better and the efficiency is more known. So it looks like the work is easier than now.
Well?
I'll echo something that Roelof started with. No matter how good the material is, you have to get it where you want it and the concentration that you wanted, and that's a critical piece that we all have to consider.
Yeah, good point.
I think it's still important to study this interplay or competition of different aerosol types for their CCN and ice activation processes under simulated cloud environments, what we can do in the lab, but it's also important, I think, to have in mind the natural seeding agents. So what I said at the end of my talk, that it's also important to understand the natural cloud processes, and that requires also longer-term monitoring and measurements of aerosol, CCN, and IMPs in the area of seeding operations, and maybe even in the cloud environment.
Excellent. Great suggestions and ideas maybe to propel future research to be done. I recognize we are out of time, and I do apologize if we didn't get to your questions, but two things. Of course, lunch is around the corner. I don't want to be an impediment there, but absolutely feel free to catch our speakers in the hallways and approach them and present some of these questions or other questions you may have had that you maybe haven't had the chance to ask here. So with that, please help us thank our speakers one more time. I think with that, Hamda, or do you want me to declare victory and we can move to lunch, or do you have other comments? Okay, we are free to eat. Thank you so much.
Thank you.
And in our next session, we will be hearing from both the next generations of scientists and researchers, as well as seasoned experts as they present their work on atmospheric research and rainfall enhancement studies. This poster session provides a platform for students and early career scientists to share their research with the global scientific community and engage in meaningful discussions with experts in the field. And this will be the last session for the day. And see you again tomorrow.